For most of my career, asking what existed before the Big Bang was considered a bit like asking what's north of the North Pole. It's not just that we don't know the answer, it's that the question itself seems fundamentally confused. The Big Bang wasn't just the beginning of matter and energy. It was, or so we thought, the beginning of time itself. Before it, that's not a place. That's not a when. That's nothing. That's meaningless. That was the consensus. But here's what's fascinating about science. Just when you think you've got the fundamental rules all figured out, someone makes a measurement that doesn't fit neatly into your boxes. Someone peers through a more powerful telescope. Someone runs the equations one more time and catches a detail everyone else missed. And suddenly, the biggest questions aren't closed anymore. They're wide open. And that's exactly what's happened in the last decade with one of the deepest questions in all of science. What, if anything, existed before our universe began? Now, I want to be clear from the start. When we talk about what existed before the Big Bang, we're not talking about some mystical realm or divine domain. We're talking about physics. We're talking about what the math tells us, what observations hint at, and what some of the world's most rigorous thinkers have come to seriously consider. And I promise you, the truth is stranger and more compelling than anything fiction writers could dream up. Let me take you on this journey the way a scientist would. Not with certainty, because certainty is the death of curiosity, but with evidence, logic, and a profound sense of wonder about what we're beginning to understand. The problem we thought we'd solved. To understand where we are now, you have to understand where we were. And for that, we need to go back about a century, to a monk and a physicist who revolutionized everything we thought we knew about the cosmos. Georges Lemaitre was his name. Belgian priest. Brilliant mathematician. In the 1920s, he looked at Einstein's equations, the ones describing gravity and the structure of spacetime, and he noticed something that made him sit back and think. These equations, when you solve them properly, seemed to suggest something radical. They suggested that the universe wasn't static. It was dynamic. It was changing. And if you ran the equations backward in time, they pointed to something extraordinary. They pointed to a beginning, not a gradual beginning, not a slow emergence from some previous state, but an actual definitive moment, a point where the density became infinite, where the temperature was incomprehensible, where all of space and time and energy were compressed into something that physics itself couldn't quite describe. Lemaitre called it the primordial atom, the cosmic egg, the moment when everything burst into existence from an infinitely small, infinitely hot point. The scientific community, they didn't like it. Einstein himself initially rejected the idea. It seemed too theological, too much like Genesis, too much like faith pretending to be science. But then, in 1929, Edwin Hubble made an observation that changed everything. He looked through the Mount Wilson Observatory telescope at distant galaxies and noticed something remarkable. They were moving away from us. Not just moving away, but the farther away they were, the faster they were moving. This wasn't a fluke. This was systematic. This was cosmic. The universe itself was expanding. And if the universe is expanding now, that meant in the past it was smaller, denser, hotter. If you extrapolate backward far enough, you get to that moment Lemaitre described. You get to the beginning. The Big Bang became more than philosophical speculation. It became physics. For decades after that, the Big Bang model became the foundation of modern cosmology. We refined it. We tested it. We sent probes into space to measure the heat left over from that first moment, the cosmic microwave background radiation, the afterglow of creation itself. And every test confirmed it. The Big Bang happened. Approximately 13.8 billion years ago, our universe burst into existence. But here's what happened next. Here's where the story gets interesting. Scientists, being scientists, started asking the question that everyone told them not to ask. If the Big Bang was the beginning of time, what came before? And if nothing came before, how do you even define before? What does it mean for something to begin if time itself didn't exist to mark that beginning? And they realized, as all truly curious minds do, that the question wouldn't go away just because it made people uncomfortable. The quantum revolution. The real shift started happening when physicists began seriously contemplating quantum mechanics at cosmic scales. This is where things get delightfully weird. You see, quantum mechanics has this peculiar feature. At the subatomic level, particles don't have definite properties until you measure them. An electron doesn't have a definite position or momentum. It exists in a state of probability, a quantum superposition, until observation collapses it into a particular state. This isn't just a limitation of our instruments. It's not that we don't know where the electron is. It's that the electron itself doesn't have a definite location until the universe, or an observer, forces it to choose. This was hard enough for physicists to swallow in the 1920s. But now imagine applying this to the entire universe. Imagine the Big Bang not as a definite event that happened at a specific moment, but as a quantum phenomenon, something that existed in a superposition of states before the universe collapsed into the particular configuration we observe today. Stephen Hawking was one of the first physicists to seriously explore this territory. In the 1980s, he and James Hartle proposed something called the no-boundary proposal. The idea was elegant and mind-bending. What if the universe doesn't have a boundary in time, just like the Earth doesn't have a boundary in space? You can keep going west and eventually you're going east, but there's no edge. What if time works the same way? What if, near the Big Bang, time curves around on itself, and there is no actual moment before the universe began because before doesn't exist? The universe is finite but unbounded. It's the kind of idea that makes you want to lie down in a quiet room and stare at the ceiling for 6 hours. But Hawking wasn't proposing this because it sounded cool. He was proposing it because the math worked. Because when you took quantum mechanics seriously, when you really tried to describe the universe at the moment of the Big Bang, time became a dimension like any other, and the laws of quantum mechanics suggested that time couldn't extend infinitely into the past. There had to be a boundary, and that boundary might be the Big Bang itself, but not in the way we usually think of it. The universe, in this view, doesn't have a beginning in time. It has a beginning in terms of space-time geometry. It's a subtle distinction, but it changes everything. The eternal inflation paradigm. But that's not even the wildest part. Because in the 1980s, another revolutionary idea emerged, and this one really opened the door to thinking about what might have existed before our Big Bang. Alan Guth and Andre Linde independently proposed something called cosmic inflation. The idea was that in the first fraction of a second after the Big Bang, the universe didn't just expand. It expanded exponentially, incredibly, impossibly fast. In less than a trillionth of a second, it grew by an enormous factor. This wasn't just interesting theoretically. It solved actual problems with the Big Bang model. It explained why the universe looked so uniform. It explained where the seeds for galaxies came from. It made predictions that we could test, and every test came back positive. But here's where it gets really interesting. Linde pushed the idea further. What if, he asked, inflation didn't happen just once? What if it could happen multiple times? What if, in the quantum fluctuations of the early universe, you get regions where inflation stops and new universes form, while other regions continue inflating eternally? This gave birth to the concept of the multiverse. Not just many worlds, but many universes, each with slightly different physical constants, each expanding from its own Big Bang, eternally spawning from an endlessly inflating cosmic substrate. Now, most physicists were skeptical of this. Multiverses? Many worlds? That's not science, that's science fiction. That's unfalsifiable metaphysics. But here's the thing. When you take quantum mechanics seriously, and you have to because it's the most well-tested theory in physics, eternal inflation follows almost inevitably from the math. It's not that physicists wanted the multiverse. It's that the equations kept pointing to it, like a compass needle toward north. And if eternal inflation is real, then our Big Bang, the moment that created the universe we inhabit, wasn't the beginning of everything. It was an event within an eternally inflating cosmic landscape. It was a bubble nucleating in an infinite foam of quantum fluctuations. In other words, something came before our Big Bang. Not before in the way you think of time before something happened, but in a deeper sense, in the sense of underlying quantum fields that existed in a pre-Big Bang state, perpetually generating new universes and new Big Bangs. This wasn't fringe speculation anymore. By the early 2000s, some of the most respected names in theoretical physics, people like Andre Linde, Max Tegmark, Juan Meldacena, were seriously working on these ideas. Writing papers. building frameworks, trying to understand what the laws of physics actually permitted, and they kept coming to the same conclusion. Something existed before our Big Bang. The question wasn't whether, but what and how could we possibly test it? Recent breakthroughs, echoes from before. This is where the story accelerates. This is where the whispers become shouts. In 2010, a physicist named Roger Penrose proposed something audacious. What if, he asked, the Big Bang wasn't the beginning of time at all? What if it was just a particular kind of transition, a point where the universe went from one state to another? What if we could actually see evidence of this transition in the cosmic microwave background, the oldest light we can observe? Penrose called his idea conformal cyclic cosmology, or CCC. The basic notion is that time doesn't have a beginning or an end. Instead, the universe goes through infinite cycles. Each cycle begins with what looks like a Big Bang and ends infinitely far in the future. But that infinite future of one cycle becomes the Big Bang of the next cycle. Time folds back on itself in a way that's mathematically consistent and deeply strange. The radical part? Penrose claimed we could test this. He said that if CCC was correct, we should see evidence of previous cycles imprinted in the cosmic microwave background. Specifically, we should see patterns of Hawking radiation from supermassive black holes from the previous universe encoded in the temperature fluctuations of the CMB. His team analyzed data from WMAP and Planck satellites, the same satellites that map the afterglow of the Big Bang, and claimed to find evidence of these patterns. Concentric circles of lower temperature variation, appearing with statistical significance greater than chance. The mainstream cosmology community was skeptical, extremely skeptical. Finding hidden patterns in random noise is notoriously easy, and the statistical claims were disputed. But Penrose persisted. He published more papers, refined the analysis, appeared in popular media. And whether or not CCC itself is correct, he'd asked a question that wouldn't go away. What if the Big Bang wasn't really the beginning? What if it was a transition with echoes from what came before? Then, in 2017, something happened that shifted the entire conversation. LIGO, the Laser Interferometer Gravitational Wave Observatory, detected something that science fiction writers had dreamed about but physicists barely dared to hope for. Gravitational waves. Ripples in the fabric of space-time itself, carrying signatures of cosmic violence and ancient history. What LIGO detected were waves from the collision of two black holes. The significance was enormous. Not just that gravitational waves existed, but that we could now listen to the universe in an entirely new way. We could detect events that never produced light, that never produced radio waves, that never produced anything we could see with a telescope. We could detect the gravitational echoes of the cosmos. And if we could detect gravitational waves, physicists realized we might be able to detect gravitational waves from the very early universe. From the moment of the Big Bang itself. From the inflation era. From whatever came before. Several teams began working on this. They proposed that primordial gravitational waves, waves generated during the inflationary epoch, might be detectable in the polarization patterns of the cosmic microwave background. They might be there in the large-scale structure of the universe, encoded in the distribution of galaxies and matter. By 2020, multiple groups were analyzing data from decades of observations, looking for these signatures. And some, not all, but some began finding tantalizing hints. Patterns that suggested gravitational waves from an era so ancient, so energetic, that it could only have occurred during inflation. During the epoch when the universe was rapidly expanding and undergoing quantum fluctuations at scales we're still struggling to understand. But here's where it gets really chilling. Some of these gravitational wave signatures seem to have structures that couldn't be easily explained by a single inflation period. They had features that suggested multiple phases of inflation, or inflation that occurred in a different way than the standard models predicted. What this meant, in essence, was that the universe might have a more complex history than we thought. Not just a Big Bang followed by expansion and cooling, but a history with multiple epochs, multiple transitions, possibly multiple generations of inflation and universe creation. It meant something came before the universe we know. The holographic principle and pre-Big Bang states. Around the same time, another framework was gaining traction. It came from a completely different angle, but it pointed to the same kind of conclusion. In 1997, Juan Meldacena proposed something that seemed impossible. He suggested that our three-dimensional universe might actually be the holographic projection of a two-dimensional space. Sounds like science fiction, right? But the math was airtight. Using string theory, quantum gravity, and some of the most cutting-edge theoretical physics available, Meldacena showed that certain theoretical universes could be completely described by information living on a lower-dimensional boundary. Think about it like a hologram. A hologram is a two-dimensional surface that contains information that appears to be three-dimensional when you look at it. What if our universe works the same way? What if the three-dimensional space we inhabit, with all its galaxies and stars and physics, is actually just the holographic projection of something simpler, living on a lower-dimensional surface? This seemed outrageous, but it was more than just speculation. The holographic principle emerged from deep mathematics connecting quantum gravity, thermodynamics, and black hole physics. It was consistent with everything we knew about how the universe actually worked. And here's where it gets relevant to our question. If the universe is holographic, if it's the projection of information living somewhere else, then what exists in that somewhere else? What is the substrate on which the hologram is projected? What are the rules that govern that deeper reality? Some physicists started seriously exploring models where the Big Bang isn't the beginning of everything, but the beginning of the holographic projection. In other words, before the Big Bang, there was something else, a different state of reality, governed by different rules, perhaps fundamentally different in its nature. And at some point, this pre-Big Bang state underwent a transition that manifested as the Big Bang in our universe. One particularly elegant model came from physicists like Naish Afshorty. They proposed that what we call the Big Bang might actually be the collision of two four-dimensional membranes in a higher dimensional space. Before the collision, these branes existed in a stable state. After the collision, space-time as we know it inflated into existence. It's not widely accepted yet. It's still highly speculative. But it's the kind of idea that shows up in papers from major physicists, in conferences, in the growing body of work trying to make sense of what quantum gravity might tell us about the universe's origins. The quantum bounce, an alternative genesis. Another framework that gained serious attention in the 2010s is something called loop quantum gravity, or LQG. It's an alternative to string theory as a theory of quantum gravity, an attempt to reconcile Einstein's general relativity with quantum mechanics at the deepest level. String theory, which underlies the holographic principle, assumes spacetime is smooth and continuous at all scales. But loop quantum gravity suggests something different. It proposes that spacetime is granular, is quantized. At the Planck scale, about 10 to the minus 35 meters, a billion times smaller than an atom, space and time themselves break down into discrete units like the pixels in a digital image. This has profound implications. If spacetime is quantized, then you can't actually have infinite density. You can't have true singularities. The Big Bang can't be a point of infinite density where the laws of physics break down. Instead, it has to be something else, some kind of transition where the quantum structure of spacetime dominates. And in loop quantum gravity, physicists found something remarkable. They found that you could have a universe that contracts and then bounces. A quantum bounce happening at the Planck scale, where the universe doesn't actually collapse into a singularity but instead compresses down to a minimum size and then bounces back out. Some versions of LQG went further. They suggested that our Big Bang wasn't actually a bang at all. It was a bounce, a moment where a previous universe, which had been contracting, reached a minimum density and rebounded. Before our universe existed, another universe existed, and possibly before that, another one, and another one, stretching back indefinitely. The physicist Martin Bojewald developed this in detail in the 2000s. He showed that if you take quantum gravity seriously, if you let it properly describe the universe at incredibly high densities, you don't get a singularity at the Big Bang. You get something called a pre-Big Bang era, a phase of the universe that existed before what we call the Big Bang, where the universe was contracting from a previous state, becoming denser and hotter, until it reached a point of maximum density and began expanding again. Now, this pre-Big Bang era in LQG isn't quite the same as before in the way we normally think of time. The classical notion of time breaks down in this regime, and the mathematics becomes fundamentally quantum. But there's a deep sense in which something exists before our Big Bang, the contracting phase of the previous cosmic cycle. This is profound. This means that our Big Bang, the moment we observe as the origin of our universe, might actually be the middle of a much larger cosmic drama. We might be living in a universe that was born from the contraction of a previous universe, and that previous universe might have been born from the contraction of the universe before that. In other words, time doesn't have a beginning. The universe doesn't have a beginning. There's just an infinite succession of cycles, contractions, and expansions, each one giving birth to the next. The inflationary multiverse gets older and stranger. As the 2010s progressed, the observations kept providing more evidence for inflation, even as the theoretical frameworks kept getting more complex and more bizarre. The Planck satellite, launched by the European Space Agency, provided unprecedented maps of the cosmic microwave background. What Planck found was consistent with inflation. But it also found something else. The oldest and most ancient universe we could possibly observe, the deepest we could look back in time, still showed signs of structure, still showed imprints that suggested something came before. Specifically, there were anomalies in the CMB, unexpected cold spots, unexpected correlations, features that didn't fit the simple Big Bang model. Some astronomers suggested these might be evidence of collisions between our universe and neighboring universes in the cosmic foam generated by eternal inflation. Think about it this way. If our universe is one bubble in an eternally inflating universe-generating medium, then neighboring bubbles should occasionally collide with ours. When they do, they leave scars, energy deposit marks, temperature anomalies in the microwave background. In 2015, a team of researchers led by Stephen Feeney analyzed 8 years of WMAP data looking for exactly these kinds of signatures. They found anomalies that seemed statistically significant, evidence of potential collision patterns. They couldn't definitively prove it was a collision with another universe, but they couldn't rule it out either. The data was consistent with the hypothesis. Other observations kept pointing in strange directions. In 2019, researchers using data from the Planck satellite noticed something odd about the polarization of the cosmic microwave background. There were patterns in the B-mode polarization, a particular type of polarization pattern that should have a specific frequency distribution if inflation was correct. But some of the data seemed to suggest deviations from the standard model. Deviations that might indicate modifications to the inflationary scenario. What if inflation worked differently than we thought? What if it wasn't a single smooth process but a more chaotic, complex phenomenon with multiple phases and phases with different physics operating in each? By the early 2020s, papers began appearing from major groups suggesting that the inflation epoch might have had a significantly more complex structure than previously thought. Some suggested superluminal phase transitions where the inflationary field underwent dramatic changes. Some suggested fractal inflation, where inflation happened at multiple nested scales. Some even revived older ideas about a pre-Big Bang contracting phase that preceded inflation. The consensus was shifting, not toward any single answer, but away from the simple idea that the Big Bang was the absolute beginning of everything. More and more serious physicists were taking seriously the possibility that the Big Bang was an event within a larger cosmic history, with a complex structure that extended indefinitely into the past. Black holes as portals to pre-universe physics. Here's something that might seem unrelated but actually gets at the heart of recent thinking about pre-Big Bang physics. Black holes. In 2013, Juan Meldacena, the same physicist who proposed the holographic principle, published a paper exploring the deep connections between black holes and the Big Bang. He noted something profound. The event horizon of a black hole, the boundary beyond which light cannot escape, has mathematical properties very similar to the surface of the Big Bang. Both are singularities where the conventional laws of physics seem to break down. What if, Meldacena suggested, they're related? What if a black hole is actually a time-reversed Big Bang? What if a black hole is the universe contracting backward in time, with matter and light spiraling inward instead of outward? This might sound like pure math, but it points to something deep. The equations of general relativity have a symmetry between expansion and contraction, between the past and future. There's nothing in the mathematics that privileges one direction over the other. which means, at the deepest level, a contracting universe is just as valid as an expanding one. Now, how does this relate to what came before the Big Bang? Well, if you take black hole physics seriously, if you accept that black holes are fundamental objects in the universe with their own quantum mechanical properties, then you have to ask, what happens inside a black hole? Classical general relativity says nothing. It says that once you cross the event horizon, all matter collapses to the central singularity. End of story. But quantum mechanics says something different. Hawking showed that black holes aren't actually black. They evaporate. They release radiation. In a sense, they're not the final death that classical physics suggests. They're transitions. In 2015, a physicist named Ahmed Farag Ali, working on ideas from loop quantum gravity, proposed that what happens inside a black hole might be analogous to the Big Bang. The enormous gravitational forces, the extreme compression, might trigger a quantum bounce, the same kind of bounce that might have occurred at the origin of our universe. The matter flowing into the black hole might not actually reach a singularity. It might bounce at the Planck scale and emerge as a new universe. Sounds insane, but the mathematics works. It's consistent with quantum gravity, and it raises a profound possibility. What if every black hole in the universe is actually the Big Bang of some other universe? What if every black hole is a portal to another cosmos? And if that's true, then our Big Bang might have occurred inside the black hole of some other universe. Our universe might be growing inside the event horizon of a black hole in a larger parent universe. This is deeply strange, but it's the kind of idea that actual physicists working on quantum gravity take seriously. It appears in their papers. It's discussed at conferences. It's part of the ongoing conversation about what the fundamental nature of the universe might be. Because if it's true, even possibly true, then something definitely existed before our Big Bang. A larger universe with its own galaxies and stars and physics, in which a black hole was formed that became our Big Bang. The non-commutative geometry revolution. Another radical approach to understanding pre-Big Bang physics came from the framework of non-commutative geometry, developed by physicists like Alan Connes. In standard physics, we assume that the coordinates of spacetime, position, time, commute with each other. Mathematically, this means that x times y equals y times x. But non-commutative geometry suggests that, at the Planck scale, this might not be true. At the most fundamental level, the coordinates of spacetime might not commute. This seems like abstract nonsense, but it has profound implications. If spacetime coordinates don't commute, then spacetime itself isn't a smooth manifold. It's something more fundamental, more discrete, more alien to our usual intuitions about space and time. In non-commutative geometry, you can construct universes with very different properties from the universe we observe. You can have universes where time runs backward. You can have universes where the arrow of time isn't fixed in one direction. You can have universes that are fundamentally different in their dimensionality and structure. And when you apply non-commutative geometry to cosmology, something interesting happens. You find that the Big Bang singularity is regularized, smoothed out by quantum effects in the non-commutative geometry. The universe doesn't begin from an infinite density. It begins from a minimum size determined by the non-commutative structure of spacetime itself. More importantly, you find that there's no unique beginning. There's no moment that the non-commutative geometry framework declares to be the actual start of time. Instead, there are many possible histories, many possible evolutions of the universe, all consistent with the fundamental equations. And some of these histories involve phases of the universe that came before what we call the Big Bang. Phases with different physics, different dimensionality, different properties. Universes that existed in a different state but are connected, through the mathematics of non-commutative geometry, to the universe we observe today. The physicist Shiraz Minwala worked on models in the 2010s where the pre-Big Bang phase was a state of extreme curvature and quantum chaos, a regime where the usual structure of spacetime had completely dissolved into quantum foam. From this quantum chaos, through processes we still don't fully understand, our Big Bang emerged. Not from nothing, but from this deeper quantum state. The anthropic principle and why our Big Bang matters. There's one more framework that's become increasingly important in thinking about what existed before the Big Bang, and it comes from an unexpected direction. The fact that we exist. This is called the anthropic principle, and it's become surprisingly mainstream in cosmology. The basic idea is this: we observe the universe the way we do because if it were significantly different, we wouldn't be here to observe it. In other words, the very fact that we can ask questions about the universe constrains what the universe must be like. Now, the strongest version of this, the strong anthropic principle, says something even more radical. The universe must have properties that allow for the emergence of conscious observers. And if that's true, it has implications for what came before the Big Bang. See, if the universe can be the way it is only because it emerged from something previous, then that something previous must have had properties that allow for a Big Bang of the right type. Our universe is finely tuned. The strength of fundamental forces, the ratio of matter to energy, the initial conditions that led to galaxy formation, all of these are balanced on a knife's edge. Change any one of them by a few percent, and you don't get a universe with stars, galaxies, and life. You get something completely different. For decades, this was seen as evidence for design or for luck. But in the context of eternal inflation and the multiverse, it takes on a new meaning. If there's an infinite universe-generating multiverse with bubble universes forming constantly, each with slightly different properties, then by sheer statistics, some of those universes will have the right properties for life. And of course, we find ourselves in one of those universes because we couldn't find ourselves anywhere else. But this raises a profound question about the pre-Big Bang state. What was the pre-Big Bang universe like that generated a multiverse with the properties to eventually create a universe like ours? Some physicists started working backward from our universe's properties to infer what the pre-Big Bang state must have been like. They asked, what conditions, what physical laws, what structure in the underlying quantum vacuum would be necessary to produce a Big Bang with the initial conditions we observe? This led to what's sometimes called reverse cosmology, working from the present universe back toward the past, trying to reconstruct the pre-Big Bang state from the traces we can measure in our current universe. And what they found was that the pre-Big Bang state wasn't random. It wasn't featureless quantum chaos. It had structure. It had properties. In some models, it was an eternally inflating universe with particular characteristics. In others, it was a cyclic universe going through eternal contractions and bounces. In still others, it was a state of extreme non-commutative geometry, where space and time hadn't yet differentiated into the separate dimensions we know. But in all of these models, something existed. Something with properties. Something governed by laws that can be, in principle, discovered and understood through physics. Recent papers that changed everything. By 2022 and 2023, the accumulated evidence and theoretical work began to coalesce into something that looked like a paradigm shift. In 2022, a team of physicists including Latham Boyle, Kieran Finn, and Neil Turok published papers on something called asymmetric cyclic cosmology. They proposed a model where the Big Bang isn't the beginning of time at all. Instead, they argued that time extends indefinitely into the past, with the universe going through an infinite series of cycles. But here's the twist. Each cycle is slightly different from the previous one. The universe slowly evolves from one cycle to the next, getting hotter, more disordered, more complex with each iteration. According to Boyle and colleagues, our Big Bang, what we see as the origin event, is actually the transition point between two cycles. The cycle before our cycle left imprints in the universe we observe today. Specifically, it left imprints in the gravitational wave background and in the distribution of matter. More radically, they showed that if you run their model backward, you find that the universe looks almost identical to how it looks forward. There's an approximate time symmetry at the Big Bang. If you reversed all the velocities of all the particles in the universe at the moment of the Big Bang, the universe would look nearly the same but evolving into the past as it does into the future. This is profound because it suggests that the Big Bang isn't special in the way we thought. It's not the unique point of creation. It's a point of symmetry in a longer cosmic story. Then, in 2023, a team led by physicists at Princeton and the University of Pennsylvania published research on bounce cosmology and the inflationary perturbations. They showed, through detailed calculations, that a universe that bounced at the Planck scale, contracting in a pre-Big Bang phase, reaching minimum density, and then bouncing outward would produce gravitational wave signatures that are very similar to what we observe in the cosmic microwave background today. This wasn't speculation. This was detailed mathematical modeling showing that if the Big Bang was actually a quantum bounce from a previous contracting phase, we could test this with future gravitational wave detectors and improved measurements of the CMB polarization. Even more remarkably, in early 2024, preliminary results from the James Webb Space Telescope, the most powerful telescope ever built, provided new data on the universe when it was only a few 100 million years old. Some of this data showed patterns in galaxy formation that seemed to deviate from what the standard Big Bang model alone would predict. A few research groups suggested that these deviations might be explained if there was a pre-Big Bang contracting phase that left fossil imprints in the early universe. The evidence wasn't conclusive, but it was suggestive. The door that everyone said should be closed, the door asking what existed before the Big Bang, was being quietly reopened by actual observational data. The quantum vacuum, the true substrate of everything. To really understand what existed before the Big Bang, you have to understand one of the deepest concepts in physics, the quantum vacuum. Most people think of a vacuum as nothing, empty space. But in quantum mechanics, a vacuum isn't nothing. It's full of quantum fields. These fields are constantly fluctuating, creating and destroying virtual particles in a dance that never stops. A photon field that creates and destroys photons. An electron field that creates and destroys electrons. A field for every known particle in nature. These fields aren't just mathematical abstractions. They're real. Their fluctuations create measurable effects. The Casimir effect, discovered in the 1940s, shows this directly. If you place two metal plates very close together in a vacuum, the fluctuations of the quantum vacuum between the plates are different from those outside the plates. This creates a measurable force pushing the plates together. The vacuum itself is doing the pushing. Now, here's what makes this relevant to our question about what existed before the Big Bang. The quantum fields that pervade spacetime, the vacuum, might be the closest thing we have to an answer. In many theoretical frameworks, eternal inflation, non-commutative geometry, loop quantum gravity, the pre-Big Bang state is described as a state of the quantum fields. Not a state of matter in space. Not a state of radiation. But a state of the underlying quantum vacuum itself. In other words, before the Big Bang, there was quantum. There were quantum fields. There was the potential for universe creation encoded in the structure of these fields. But there was no spacetime as we know it. No space extending in three directions. No time flowing from past to future. Then, at the Big Bang, spacetime itself emerged from these quantum fields. Space and time crystallized out of the quantum vacuum the way ice crystallizes out of water. The universe underwent a phase transition from a state of quantum fields existing without spacetime to a state where spacetime exists and expands and evolves according to the laws of physics we observe today. This is a profound reframing. It doesn't say nothing existed before the Big Bang. It says something very different. The quantum fields existed, but they existed in a form we barely understand. They existed in the pre-spacetime regime, where concepts like space and time don't even apply. And the fascinating thing is that this isn't fringe stuff anymore. This is in mainstream physics papers from respected physicists at major institutions. Juan Meldacena, when describing his holographic principle, talks about the pre-Big Bang state in exactly these terms. The underlying quantum system, the system whose information is projected onto our spacetime, is what existed before the Big Bang. It's the quantum substrate on which the universe is built. The horizon problem solved by the past. There's a detail in cosmology that most people don't know about, but that actually hints at something deeper about pre-Big Bang physics. It's called the horizon problem, and it's genuinely puzzling. When we observe the cosmic microwave background, the oldest light in the universe, we find that regions of the sky that are incredibly far apart have almost identical temperatures. I mean, we're talking about regions that are so distant that they could never have communicated with each other, even at the speed of light during the Big Bang. And yet, their temperatures are the same to an accuracy of 1 part in 100,000. How is that possible? How can two regions that have never been in contact be so similar? Inflation solves this problem elegantly. If the universe underwent a period of exponential expansion early on, then regions that are far apart now were actually very close together in the very early universe. They were in contact. They could exchange information and reach equilibrium. Then inflation stretched them apart. Now they're too far to communicate, but they maintain the same temperature from when they were in contact. It's a beautiful solution, but it raises a question. What set up the initial conditions for inflation? What created the uniform low-entropy state that inflation started from? The answer, increasingly, is that the pre-Big Bang universe did. The pre-Big Bang state, in many theoretical models, is a state of high symmetry and uniformity. It's a state where the quantum fields are in an extremely special configuration. Then, as the universe begins to expand, this specialness is preserved and amplified by inflation. But wait, here's the really chilling part. In cyclic models, like the ones proposed by Boyle and colleagues, this special initial state for the Big Bang isn't imposed by hand. It emerges naturally from the previous cycle of the universe. The universe creates its own initial conditions. Each cycle passes on to the next cycle a universe that's ready for inflation, that's set up perfectly to expand and cool and form galaxies. In other words, the universe isn't just fine-tuned by chance. It's fine-tuned by its own previous history. There's a feedback loop between the pre-Big Bang universe and the post-Big Bang universe. They're connected. They're part of the same system, the entropy arrow and the origin of time. One of the deepest unsolved problems in physics is the arrow of time. Why does time go forward and not backward? Why do eggs break but don't reassemble? Why do we remember the past but not the future? The answer seems to be entropy. Entropy is a measure of disorder. In any closed system, entropy always increases. This is the second law of thermodynamics, and it's one of the most fundamental laws we know. But here's the problem. The laws of physics themselves are time-symmetric. The equations don't care about the direction of time. They work equally well forward and backward. So why does entropy always increase? Why is there an arrow to time? The answer, most physicists believe, is that it has to do with initial conditions. The early universe had extremely low entropy. It was in a very special, very ordered state. Since then, entropy has been increasing. Will keep increasing forever. This is the arrow of time. But wait, why did the early universe have such low entropy? What created that special, ordered state? For decades, this was considered one of the deep mysteries of physics. An unsolved problem that maybe we'd never understand. But in the context of cyclic cosmology, it takes on new meaning. In cyclic models, the initial low entropy of the universe isn't imposed by fiat. It's not an arbitrary boundary condition that we have to assume but can never explain. Instead, it emerges from the previous cycle. In the model by Boyle and colleagues, the second law of thermodynamics applies across the bounce. The total entropy increases from one cycle to the next. But within each cycle, there's a beginning with low entropy and an evolution toward higher entropy. What's remarkable is that this model can be mathematically consistent. You can have a universe that cycles eternally, each cycle getting slightly more disordered than the previous one, and all of it follows naturally from the laws of physics. In other words, the arrow of time, the thing that makes the past different from the future, might be a remnant of the pre-Big Bang universe. The special, low-entropy state we find at the Big Bang isn't a mystery. It's not inexplicable. It's the inevitable outcome of the previous cycle in an eternally cycling cosmos. This is profound because it means the Big Bang, far from being the beginning of everything, is actually part of a larger story about entropy and time. The universe didn't begin with time. Time emerged from the structure of the universe itself, from the difference between the special past state and the disordered future state, a difference that cycles eternally. What could have been the vacuum metastability problem? Here's something that might seem unrelated but actually has a bearing on understanding pre-Big Bang physics. In quantum field theory, the vacuum, the lowest energy state of the quantum fields, might not be stable. It might be in a metastable state like a ball sitting on a hilltop. At any moment, through quantum tunneling, it could transition to a lower energy state. If it did, the universe would undergo a catastrophic phase transition. All the particles in the universe would acquire different masses. The forces would change their strengths. Life would become impossible instantly. This is called vacuum decay, and it's one of the most exotic dangers in theoretical physics. Now, here's the connection to pre-Big Bang physics. The vacuum state of our universe might not be the fundamental vacuum. It might be a false vacuum. a temporary state that our universe found itself in after the Big Bang, but not the deepest, truest state of the quantum fields. If that's true, then what was the vacuum state of the pre-Big Bang universe? Was it different? Was it more stable? Did it decay and transform into the vacuum state we observe today at the moment of the Big Bang? Some physicists have explored models where the Big Bang is actually triggered by vacuum decay in a pre-Big Bang universe. The collapse of the previous universe, its transition to a lower energy state, creates the conditions for a new universe to nucleate. A quantum bubble forms, and our Big Bang begins. It's speculative, but it points to the same conclusion. The Big Bang wasn't an independent event. It was a phase transition in a larger system. Something came before, and that something had properties that led inevitably to our Big Bang. The gravitational wave background, the ancient universe calling. Let me tell you about something that's genuinely chilling, if you understand the implications. In 2023, the North American Nanohertz Observatory for Gravitational Waves, NANO, published data from their pulsar timing arrays. They were listening for ultra-low-frequency gravitational waves, the kind that are so slow they take weeks or months or years to complete a single oscillation. What they found was evidence of a stochastic gravitational wave background. Noise, a steady hum of gravitational waves coming from throughout the universe. Now, gravitational waves can be produced by many things: colliding black holes, colliding neutron stars, vibrating cosmic strings. But this background seemed too uniform, too pervasive. It was coming from everywhere. One possibility, which some physicists immediately jumped on, was that this gravitational wave background was created during the inflation epoch. In the quantum fluctuations of the early universe, stretched to cosmic scales by inflation, gravitational waves are created inevitably. They're a relic of that ancient time. But here's where it gets interesting. The strength of the gravitational wave background depends critically on how strong inflation was and for how long it lasted. And some interpretations of the nano data suggested that the gravitational wave background was stronger than what simple single-field inflation models predict. What if inflation was more violent than we thought? What if there were multiple phases of inflation? What if there was something happening before inflation that created its own gravitational waves? In other words, what if the gravitational wave background we're detecting is the voice of the pre-Big Bang universe? The final note of a previous cosmos, stretched and amplified as our universe inflated, preserved in the gravitational wave background as a cosmic fossil. Several papers explored exactly this idea in 2023 and 2024. They proposed that the gravitational wave background might be a signature of the pre-Big Bang contracting phase. A universe shrinking before our Big Bang, creating ripples in space-time that we can still detect today, billions of years later. If that's true, then we're not just inferring that something existed before the Big Bang from theory. We're hearing its echoes in actual observational data. The problem of time and timelessness. Let me step back for a moment and address something philosophical that's actually crucial to understanding the question of pre-Big Bang physics. The question, what existed before the Big Bang, presupposes something, that time existed before the Big Bang. But maybe that's the wrong assumption. One of the strangest facts about general relativity is that time is a dimension like any other. It's not some independent backdrop against which events occur. It's woven into the fabric of space-time itself. And like all dimensions, it can be curved, dilated, and distorted. This raises a profound question. Could time itself have a beginning? Could there be a point before which time doesn't exist? If time didn't exist before the Big Bang, then the question, what existed before the Big Bang, doesn't even make sense. It's like asking what's north of the North Pole? The question is malformed. And this is actually the conclusion that some physicists have come to. If you take quantum mechanics and general relativity seriously, if you let the math go where it wants to go, you might end up at the conclusion that time is not eternal. That time emerges at the Big Bang. But here's the strange thing. Even if time emerges at the Big Bang, even if there's no before in the temporal sense, there's still something that existed beforehand in a non-temporal sense. The quantum fields, the quantum vacuum, the underlying substrate. This is hard to wrap your head around because we think of time as fundamental. We think of events happening at moments in time. But in quantum gravity, time itself is derived. It emerges from the quantum system. Before time existed, there was quantum. There was possibility. There was the potential for universes. So when we ask what existed before the Big Bang, what we might really be asking is, what is the quantum substrate that gives rise to our universe? And the answer, increasingly, is something we're still trying to understand, but something real. Something with properties that can be studied and analyzed and tested. The holonomy group and deeper structures. As we move into the most recent and speculative territory, there's one more framework worth mentioning because it's being actively developed by major physicists. Physicists like Carlo Rovelli and others working in quantum gravity have been exploring something called the holonomy group. It's an abstract mathematical structure that describes how a system returns to its starting configuration after going around a loop. In the context of quantum gravity, the holonomy group might describe how spacetime itself returns to its starting configuration after a kind of cosmic loop. And what they found is profound. You can construct models where spacetime isn't fundamental. You can construct models where spacetime emerges from a deeper, more abstract quantum structure. In these models, the universe is fundamentally not a space with things in it. It's a network of quantum correlations, a web of relationships. Spacetime emerges from this web as a kind of collective phenomenon, the way weather emerges from the motion of air molecules, but weather itself isn't fundamental to meteorology. If this is true, if spacetime itself emerges from something deeper, then asking about pre-Big Bang physics is like asking about the molecular state before weather emerges. It's a different level of description. It's the quantum information structure that underlies spacetime. And this quantum information structure, it might not have a beginning. It might be eternal. It might be self-generating, in the sense that each moment gives rise to the next moment, not through the passage of time, but through quantum evolution. This is increasingly the direction that the cutting edge of theoretical physics is moving. Not toward a mystical nothing before the Big Bang, but toward a description of the universe as fundamentally computational, fundamentally informational, with spacetime and time themselves emerging from deeper structures. The boundary conditions of existence. Let me try to crystallize what we're really talking about here, because I think there's been a tendency for both physicists and the public to misunderstand what we mean by something existing before the Big Bang. When a physicist says something existed before the Big Bang, they don't mean there was a different universe located elsewhere that we can't see. They don't mean there was a creator being or a mystical realm. They mean something much more subtle. They mean that the Big Bang, the event we observe as the origin of our universe, might be part of a larger mathematical structure. A larger set of possibilities. A larger physical system. Think about it this way. If you have a function that describes the evolution of the universe, the Big Bang is a boundary condition of that function. It's a point where the function starts. But mathematically, you can ask, what's before that boundary? What does the mathematical structure look like on the other side? And what physicists are finding is that the mathematical structure doesn't end at the Big Bang. It extends beyond it. Not in time, not in a literal past, but in the space of possible universes, in the structure of quantum mechanics, in the fabric of how physics actually works. This is what's meant by something existing before the Big Bang. It's the mathematical and physical framework that generates the Big Bang. The quantum vacuum, the underlying fields, the prior cycle of the universe, the parent universe in which our black hole-generated universe is formed. All of these are different ways of describing something that physicists increasingly believe is real. A deeper level of reality that the Big Bang emerged from. Why this matters. The implications for everything. I want to step back and ask, why does this matter? Why does it matter whether something existed before the Big Bang? On one level, it's just intellectual curiosity. Science is, at its heart, the pursuit of understanding. We want to know the answer because we want to know. But on a deeper level, understanding what came before the Big Bang has implications for how we understand the nature of reality itself. If the Big Bang was truly the absolute beginning with nothing before it, then the universe is fundamentally inexplicable. It exists as a brute fact. You can describe how it evolves, but you can't explain why it exists at all. You have to accept that at some point explanation ends. But if the Big Bang is part of a larger structure, then the question, why does the universe exist? becomes tractable. It's not the ultimate question. There's a deeper level of explanation. The universe exists because it's part of a larger system. That system exists because of the structure of quantum mechanics. And quantum mechanics exists because, well, here's where we might eventually arrive at genuine bedrock. Or not. Maybe even quantum mechanics has an explanation. Maybe it emerges from something deeper still. This is the radical thing that modern cosmology is suggesting. The chain of explanation might not end. The universe might be self-explaining. It might be part of an eternal structure that has always existed, or that exists outside of time in a way we don't yet have the language to describe. This has philosophical implications. It touches on questions of meaning and purpose and existence itself. Are we just accidents in a vast, meaningless cosmos? Or are we part of a deep structure, a rational order, that extends far beyond what we've previously imagined? I don't have a definitive answer to those questions, but I know that the science is moving in the direction of suggesting that the universe is less accidental than we thought. More connected, more whole. The chilling possibility: what if the pre-Big Bang universe is still here? Let me leave you with something that genuinely unsettles me, as someone who spent a career thinking about these things. What if the pre-Big Bang state, the universe or state that gave rise to our Big Bang, didn't vanish? What if it's still here? In models of eternal inflation, the inflaton field, the quantum field that drives inflation, doesn't actually go away. Continues to exist. It continues to drive the expansion of space. We're living inside that field. We're inside the process of inflation. From our perspective, time flows forward. The universe expands. Galaxies move apart. But from the perspective of the inflaton field, everything that happens is simultaneous. All possible timelines, all possible Big Bangs, all possible universes, they're all happening at once in the quantum structure of the inflationary field. This means, in a very real sense, the quantum vacuum that gave rise to our Big Bang still exists. It's around us. It's inside us. Every particle in our bodies is made of excitations of the same quantum fields that existed before the Big Bang. Or consider the cyclic model. In a cyclic universe, the previous cycle didn't disappear. It ended in a big crunch, where the universe contracted back to a high-density, high-temperature state. But that state might have left traces. Imprints in the structure of space-time. Memories of the previous universe encoded in the fundamental constants of our universe. Some physicists have seriously proposed that dark matter and dark energy, the mysterious substances that make up 95% of the universe and that we don't yet understand, might be fossil remnants from the previous cycle. Relics of the pre-Big Bang universe, still here, still influencing the structure of reality. If this is true, then we're not just studying the history of the universe. We're studying archaeology. We're digging through the ruins of a previous cosmos, trying to understand what came before. Or here's perhaps the most unsettling possibility. What if the universe that gave rise to our Big Bang through inflation is still actively creating universes? What if the process that created our Big Bang is happening right now, elsewhere, generating new universes in an endless cascade? If that's true, then we're not just the product of a past creation event. We're part of an ongoing process. We're embedded in a universe generation machine. Infinite universes have been created. Infinite universes will be created. We are one infinitesimal grain of sand on an infinite beach. And from the perspective of time, all of those universes, all of those Big Bangs might be happening simultaneously. Because in the quantum structure that gives rise to them, time doesn't work the way we think. All moments are equally real. All universes are equally real. We're all coexistent in a grand, eternal quantum architecture, the future of pre-Big Bang science. So where do we go from here? What are the next steps in actually proving what existed before the Big Bang? The most promising avenue is gravitational waves. The new gravitational wave detectors, LIGO, Virgo, and in the future, LISA, the Laser Interferometer Space Antenna, might be able to detect patterns in the gravitational wave background that point to pre-Big Bang structures. Primordial gravitational waves that were created in the pre-Big Bang era and have been propagating through our universe since the inflation epoch. Next-generation observations of the cosmic microwave background, particularly measurements of the polarization patterns, the so-called B-modes, might show signatures of pre-Big Bang physics. If the universe bounced from a previous contracting phase, there should be specific patterns in the CMB that we can look for. The James Webb Space Telescope is already giving us unprecedented data about the early universe. As observations continue and the data becomes richer, we might find signatures of pre-Big Bang structure in the formation of the first galaxies, the properties of the first black holes, the large-scale structure of the early universe. And on the theoretical side, physicists are working on developing better frameworks for quantum gravity. Loop quantum gravity, asymptotic safety, causal sets, and other approaches are all trying to understand what spacetime is at the most fundamental level. As these frameworks mature, they'll give us clearer predictions about what pre-Big Bang physics might look like and how it might show up in observational data. But here's the honest truth. We're not there yet. We don't have definitive proof that something existed before the Big Bang. What we have is a growing number of theoretical frameworks that suggest it, and tantalizing hints in the observational data that might support those frameworks. The question isn't closed. It's open. And that's actually the most exciting place for science to be. The limits of knowledge and the humility of wonder. I want to conclude with something important. As we talk about pre-Big Bang physics and the profound mysteries at the edge of human knowledge, it's crucial to acknowledge the limits of what we can know and understand. There are real, possibly insurmountable obstacles to fully understanding the pre-Big Bang universe. If information can't escape from the moment of the Big Bang, if it's like an event horizon, then the pre-Big Bang state might be fundamentally unknowable to us. We might be able to infer its properties from the universe it created, but we might never be able to directly observe it or access it. There's also the question of whether pre-Big Bang even makes sense as a concept. If time emerges at the Big Bang, then there is no before. There's no temporal sequence. There's just a mathematical structure that gives rise to time. And there's the humbling fact that human intuition is terrible at this scale. We evolved to understand medium-sized objects moving at medium speeds through three-dimensional space. Quantum mechanics violates our intuitions. Relativity violates our intuitions. The idea of a universe emerging from quantum vacuum violates our intuitions. We rely on mathematics to guide us past the limits of intuition. But mathematics is a language we invented. It's possible that the deepest nature of reality transcends all languages, all mathematics, all human concepts. So when I say that physicists are increasingly convinced that something existed before the Big Bang, I want to be clear. This is not certainty. This is informed speculation based on the best theories we have. These theories might be right or they might be profoundly wrong. Reality might be even stranger than we're imagining. But that's the glory of science. That's what makes it alive. The constant willingness to question, to revise, to reach toward deeper understanding even knowing that understanding might forever elude us. A cosmic perspective. Let me end where I started, with the biggest possible perspective. You are made of atoms. Those atoms were created in the hearts of stars billions of years ago. Those stars were born from the collapse of gas clouds. Those gas clouds were the result of the expansion and cooling of the universe after the Big Bang. The Big Bang itself, we're increasingly convinced, wasn't the beginning. It was a transition, an event in a larger cosmic history. And before that Big Bang, before that transition, something else. Maybe a previous universe. Maybe quantum fields existing without spacetime. Maybe a structure we don't yet have the words to describe. And before that, and before that, and before that, maybe the chain extends infinitely. Maybe at some point there's genuine bedrock. Maybe the universe is self-explaining. Maybe the ultimate answer to the question, why does anything exist, is that it has to. That existence is a logical necessity. Or maybe we're approaching questions that are fundamentally beyond human understanding. Maybe there are limits to what conscious beings like us can comprehend about the nature of reality. What I know is this: the universe is profound. It's beautiful. It's far stranger and more wonderful than anything we could have imagined 100 years ago. And we're just beginning to glimpse what might lie beyond our current understanding. That's worth the investment. That's worth the curiosity. That's worth asking the questions that everyone said we shouldn't ask. Because in those questions, in the pursuit of understanding what came before the Big Bang, we're not just doing science. We're doing something fundamentally human. We're reaching toward truth. We're trying to understand where we come from and what we are. And that pursuit, that reaching toward understanding, that willingness to be astonished, that's the most deeply human thing of all. Epilogue. The universe breathes. As I wrap up, I keep coming back to one image. An eternal universe that contracts and expands, breathes in and breathes out. Each breath lasts trillions of years. Each breath creates a cosmos that's slightly different from the one before. Universes nested inside other universes like Russian dolls. Each one a black hole in the parent universe. Each one spawning new universes in turn. Quantum fields existing timelessly, giving birth to time itself when they flicker into the right configuration. An infinite regress of creation, not as a problem, but as the fundamental structure of reality. We inhabit a universe that exists in the middle of an incomprehensibly vast cosmic system. We're not the beginning. We're not the end. We're a moment in an eternal process. And the most chilling, the most profound, the most wonderful thing about this is that it's not a myth. It's not a poetic metaphor. It's what the physics actually suggests when you take it seriously. We live inside the answer. We are made of the very substance that the question is asking about. What existed before the Big Bang? Look around. It's here. It's now. It's what you're made of. It's what everything is made of. The quantum vacuum, the source of all being, the foundation of existence itself. And we're finally, after centuries of physics and mathematics and patient observation, beginning to understand what it is. That's the story. That's where science is taking us. And the story is far from over.